And now I'll do the share screen, get that set up. A plugin is required. So this requires me to install a plugin about every 2 or 3 times I do this. Fortunately, it doesn't take very long. All right, let's do this then. Okay. Let's see here. How do I do this now? This is wrong. Let me turn this upside down. How do I do this? This is what I want. All right, good. Yeah, I'm going to start a couple of minutes early because I've got some things to review from last time. So we were talking about coherent states, and here's kind of a summary of it. We start with the story of the ground state of the harmonic oscillator, which in Ket language is just 0. If you put it in a wave function, here it is. This is the normalized wave function. This is all in the units where m equals h bar equals omega equals 1. This wave function has expectation values of both position and momentum equal to 0, and it has dispersions in x and p given by 1 over root 2, which means the product of delta x delta p takes on the minimum value, which is 1/2. So this ground state is a minimum uncertainty wave packet, and moreover, the dispersions in x and p are equal to one another. So the fact that it's minimum uncertainty with equal dispersions in x and p qualifies it as a coherent state. It's a particular example of a coherent state, namely one in which the expectations of x and p are equal to 0. You can visualize it as a blob in phase space that's centered at the origin, because that's the average value of measurements of x and p with some spread around that. That's what the blob indicates to indicate the dispersions in delta x and delta p. This is just kind of a schematic representation of the quantum state. One of the purposes of coherent states, one of the ways that it's used in current literature, is to explore the classical limit. The basic idea is that in classical mechanics, x and p can be localized as finely as you want, in principle, to arbitrary precision. And although there's a limit to that in quantum mechanics, by minimizing that limit, getting minimum uncertainty wave packet, one can argue that you have something that's as close as possible in quantum mechanics to a classical state. And so for that reason, coherent states are used for this purpose, for exploring the classical limit. However, in general, you need to have expectation values of x and p not 0. You need other values. So we need to change the values of x and p. And one of the ways of doing that is to use translation operators. Here, T of A is a translation operator in position, and S of B is a translation operator in momentum. And their actions on T acting on position and momentum space wave functions, and S acting on position and momentum space wave functions, are given by these 4 formulas here. And so roughly the idea then is you can, in a sense, move this coherent state in phase space from the origin. You can displace it in x and then in p to get up to a new location that's got coordinates a and b here like this in phase space. Or you could do it in the reverse order, doing the momentum displacement first and then the position displacement. And if you do that, you find the answers are not the same, because T of A and S of B don't commute with one another. If you reverse the order, there's a phase factor which appears, which notice is proportional to the area of the rectangle in question here. So it's kind of like a Bohr-Sommerfeld phase in that sense, you see. But in any case, they don't commute with each other. And so to get the final answer of the coherent state at the location you want, it's actually path dependent. So we need to worry about the path involved. And one of the ways of handling that, at least to get a well-defined definition of a coherent state, is to introduce what we call the Heisenberg operators. Heisenberg operators are called W, and they have the same exponents as the translations in x and p, except the 2 exponents are put up together as a linear combination. In other words, it's both the exponents the exponents are together in a single exponential. And roughly speaking, the idea then is a W just does a direct translation as the crow flies from the initial to the final location in phase space. You might compare this with a product of T times S or the product of S times T, which are given by these factors like this. Now, there's an issue which is making its appearance here, which is one that that occurs more than once in this course. We'll have opportunity to talk about it more than once, and that is that this has to do with the exponentials of operators. If you have ordinary C numbers, let me summarize it down here. If you have C numbers, let's call them A and B, then ordinary numbers, in other words, then of course it's true that e to the A times e to the B is equal to e to the A plus B. This is just the usual rules of exponentials in algebra. On the other hand, if these are operators and they don't commute with each other, then this equation is not true anymore. There's something else that goes on. And in fact, in general, it's more difficult to combine together the exponentials of non-commuting operators. That's just what you see here, because one's got a momentum and the other's got a position, and they don't commute. So the product of these two is not equal to this W operator, nor is it if you do it in the other way. That isn't either. In fact, these two products aren't the same with each other. So what we like to do is to work out what W is, and then we can start to use it to create coherent states and play games with them. And that's going to be that's going to be the outline of the beginnings of this lecture tonight. All right, so I think that summarizes where we were at the end of the hour last time. Are there any questions about that before we get started on new stuff?
I had a question.
Sure.
So on the first paper that you had, the first review paper.
Yeah, I'll bring it back. Let's see if I can find it here. I'll bring it back. Yes.
So you had the like the first plot of phase space, and then you said the dispersion of X is equal to the dispersion of P, which is 1/√2.
Yes.
How do you then get, like, how do you understand the uncertainty relation? Like, is this for a classical thing? Or actually, wait, I don't think it would make sense as a classical thing.
Well, the circular blob that I'm drawing here is not intended to be a rigorous thing. It's just a visual representation that gives you an idea of the fact that this wave function, of course, represents an ensemble, and making measurements in an ensemble, the average values of X and P are 0. That's why I centered the blob at the origin and phase space. But the individual measurements don't give you measurement of X and P don't give you 0. There's fluctuations about them, either one or the other, delta X or P. And this blob is supposed to indicate the fluctuations about the mean that result from measurements on that ensemble. This is not intended to be something precise. It's just to give you an idea of the kind of thing we're talking about. Does that help? Does that help answer your question?
Yeah, I guess I'm just confused about, like, how does the H bar come in, like when you multiply delta X and delta P?
Well, we're using units here in which H bar is equal to 1. If I didn't have that, this would be H bar. These would be, yeah. If I did, so actually, you're raising an important point, which I'm glossing over in lecture. It's described in more detail in the notes. If we went to ordinary units, so we went back to real units, then X and P don't even have the same dimensions. And so to say delta X equals delta P is actually not meaningful. As it stands, you'd have to put in factors here of, factors of M, H bar, and omega, and so on to make the two things dimensionally equal. Now that can be done with reference to a definite oscillator that has a definite frequency and mass and so on, and of course definite value of H bar. So if you like, this relationship here is defined relative to what you might call a reference oscillator. Sometimes people talk about squeeze states. If you do quantum optics, you'll learn about them. A squeeze state would be one in which delta X and delta P are still equal to 1/2, but the dispersions are not equal to one another. Like delta X could be 1/2 and delta P could be 1. That's squeezed in the sense that it's squished together in X space more narrowly than the ground state of the harmonic oscillator. That means in momentum space, it's more spread out. The product has to be the same if it's minimum uncertainty. Right. So this is like talking about the ground state of a different oscillator, you see. So this is a way of saying that you need a reference oscillator in order to talk about the coherent state in question. Okay. Take a look at what's the comments that are in the notes about that. I think it's explained pretty well in there.
Okay, thank you.
All right. Well, that's a good question. All right. Now, so as I say, then the immediate goal for tonight then is to work out the Heisenberg operator to work out what this is, and to be able to evaluate its action so here's the ground state 0 here. We want to apply W to it and map it into a new state up here, which I can call AB, label it by its expectation values. W moves it like that. In other words, we could say W of A comma B acting in the ground state of the harmonic oscillator equals A comma B, where this notation here, this final notation, just represents the result of that translation in phase space. So in order to carry this process out, I'm going to tell you about what's called Glauber's theorem. Glauber's theorem is a theorem which is useful in some contexts for combining together exponentials of non-commuting operators. And what it says is that if we have two operators A and B, which commute with their commutator, A comma B, commutator of A with B, then we have the following result, is that e to the A times e to the B is equal to e to the A plus B plus 1/2 of the commutator with A with B. And so that's Glauber's theorem. And we'll get to use it quite a bit. You may notice that if A commutator is 0, so these are ordinary C numbers, and the second term drops out and you get the usual result for ordinary numbers. So here, let me prove the theorem. I'm going to prove it by some of the same techniques that were used in that very first homework problem. Let's define an operator which is a function of a parameter lambda. We'll make it e to the lambda A times e to the lambda B. And this has an initial condition that f of 0 is equal to 1, as you can see just by substituting lambda equals 1. Now then we get a differential equation for this, df d lambda, differentiating two factors using a chain rule. In the first one, I'll bring the a down to the left, so I get a times e to the lambda a. And then I'll copy the e to the lambda b. And then the second one, I differentiate the second factor, so I get e to the lambda a. And then I get a factor of b times e to the lambda b. Let's write it that way. All right. Now then, in this second factor, allow me to insert a product e to the minus lambda a times e to the plus lambda a, which of course is just 1. I do that because in this first factor here, you see you've got e to the lambda a, e to the lambda b, which is the same thing as f. And by making this insertion here, I've got the same product e to the lambda a, e to the lambda b on the right-hand side of the second factor. And so this whole thing can be written this way as a plus e to the lambda a times b times e to the minus lambda a. That whole quantity is multiplied times f of lambda, like so. All right. Now then, so far I haven't made any. So far I haven't done much. I haven't used the assumptions in the theorem, but now I'm going to do that. This product of operators here was one that appeared in the very first homework problem. And I hope by now you remember, and it's not too late to remember, that this can be expanded in a Taylor series. And the first term is b, and then you get lambda times the commutator of a with b. And then you get basically an exponential series of iterated commutators. Second term has got a commutator with a with b, and so on like this. This was a series that was worked out in that homework problem. On the other hand, Glauber's theorem assumes that A commutes with its mutual commutator of A with B. And so that means that this second factor here is 0. The lambda squared term is 0. In fact, so are all the higher order terms in that series. All of them go away. And the only thing that's left is the first two terms. And so what that means is we have an expression df d lambda is equal to the following. It's A plus B plus lambda times the commutator of A with B. That whole thing then multiplies onto f of lambda. All right. Now then, let me draw a line here. Now, to understand the following step, it helps to take a look at an expression where we have dd lambda of e to the power of x of lambda. So x here is some operator which is parameterized by a parameter lambda, and we wish to evaluate this derivative. So here's a question that arises when you're doing such an evaluation. I'll put a question mark here. Is this equal to x prime times e to the x of lambda, or is it equal to e to the x of lambda times x prime, where x prime just means the lambda derivative of x? Is it equal to either one of these two things? In other words, can you bring it down to the derivative down to the left or down to the right? If this was C numbers, you could do that, but is this true for operators? Well, we answer the question by taking this derivative here and expanding out the exponential series. So this is 1 plus x 1/2 x squared plus dot, 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 and we apply dd lambda to that. The first term gives us 0. The second term gives us x prime. The third term gives us 1/2 x prime times x plus x times x prime, where you see I've differentiated x squared again using a chain rule. The next term is going to be 1/6, and I'm going to have x prime x squared plus x prime x plus x squared x prime. You see you get 3 terms differentiating the three x's that are in the factors and so on like this, dot, dot, dot. And so what you can see is the derivative of this exponential actually doesn't equal to either one of these two answers unless you're able to migrate the x primes to the left and to the right, or to the right in these expressions here. And that will be the case if x prime commutes with x. So these things are actually okay if x commutes with its own lambda derivative, x prime commutator is equal to 0, then these results are true. Otherwise, they generally aren't true. Okay. Now then, let's go back to this expression we have here. Let's write dx d lambda is equal to a plus b plus lambda times the commutator of a with b. If I do that, then integrating with respect to lambda says that x is equal to lambda times a plus b plus lambda squared over 2 times the commutator of a with b, like so. And so then the question then is, the question then is this is the differential equation we want to solve up here. Can I write this in the form of df d lambda is equal to x prime times e to the x? Does that work? Well, it'll work if x prime, which is dx d lambda, commutes with x. So the question devolves into asking whether these two lines commute with each other. Well, in fact, they do, because any operator commutes with itself. So a plus b commutes with a plus b, and the commutator of a b with itself commutes with itself. And a plus b commutes with the commutator because that's what we assumed in Glauber's theorem. And the same thing applies to the other cross term. So in fact, we have commutator x prime with x is equal to 0 for this example. And so I don't need to have a question mark here. This is a check. And in fact, what this implies is that f is equal to e to the x, namely f is equal to, let me bring it on another page. It implies that f of lambda is equal to e to the lambda times a plus b plus lambda squared over 2 times the commutator of a with b. And you'll see that satisfies the initial conditions, f of 0 equals to 1. And if I set lambda equals to 1 here, setting lambda equals to 1, that gives me the answer we want, which is the statement of Glauber's theorem right there. Okay. So Glauber's theorem is actually a very special case in which it is reasonably easy to combine exponentials of non-commuting operators, but in fact, it covers the cases that we need to deal with tonight. So I'll show you now how we can use this theorem. Let's apply this to the operator t of a times s of b, which is equal to e to the minus ia p hat times e to the plus ib x hat. And let's let capital A be equal to minus ia p hat and capital B be equal to plus ib x hat, which of course are the exponents here. So this becomes e to the a times e to the b, or with these definitions. Now the commutator of a with b is equal to, you can work it out easily because I minus I times plus I is just 1. A times B just gives me AB. And the commutator of P with X is minus I. So this is equal to minus IAB. That's the commutator. And that commutator is a C number, and which therefore commutes with everything. So in particular, it commutes with A and B, and thus the conditions of Glauber's theorem are met. And thus this thing becomes equal to e to the minus I A P hat plus I B X hat minus I A B over 2 on the basis of Glauber's theorem. The last factor is a C number, so it commutes with everything. So I can actually factor it out from the exponentials and write this as e to the, it's really a phase factor. As you can see that last factor like that. And if what's left over here, the first factor here is the Heisenberg operator. That's W of A comma B. And thus what we find is that W of A comma B is equal to E to the IAB over 2 times T of A times S of B. And if you work it out, you'll find it's equal to E to the minus IAB over 2 times S of B T of A if you put it in the reverse order. But in any case, this now gives us an explicit formula for the Heisenberg operator W. Now then, now we're almost done and ready to start creating coherent states, as many as we want. Let's call the state AB. I think I wrote this down previously. Is W of A comma B applied to the ground state 0 of the harmonic oscillator. Well, these T of A and S of B's are easy to work out. We have the wave function for psi of 0, and then multiplying by a phase factor is easy. So I'll just quote the answer for you. Let's call it psi sub A of B of X. The normalization is the same. It's 1 over pi to the 1/4 power. That's what the prefactor is supposed to be. Then it's e to the minus x minus a quantity squared over 2 plus IB times x, and then minus IAB over 2. Now I won't really use that wave function in the rest of my lecture tonight, but I'm going to box it anyway because it's nice to get the result, to get the actual wave function. And this is the wave function of the coherent state, which has now been moved to an arbitrary position in phase space. The dispersions delta x and delta p didn't change because the Heisenberg operators don't change the dispersions. On the other hand, the expectation values of x and p do change because they change under a Heisenberg operator in the following way: is that applying a W A comma B to this will map expectation value of x into itself plus an A, and if P gets mapped into itself plus a B. It's really just because it's a combination of position and momentum translation operators, and each one does one of the two of these two expectation values. All right.
Oh, sorry. In proving Glauber's theorem,
Yes.
so earlier we reached to like dfd lambda equals some stuff times f of lambda, but then later on it seemed like we wrote dxd lambda equals just that stuff, not times x. So
No, it should be e to the x. You see, the idea is if f is equal to e to the x, then this thing and this thing is dx d lambda, then you need, for this equation to be true, you have to show that x and x prime commute with each other. So the supposition here is we'll write f of lambda is equal to e to the x.
okay.
You see? Yeah.
All right, thank you.
So it's a way of just checking out that exponential, but being careful that you have to check that commutator to make sure the algebra is right. The algebra would be right for C numbers, but for operators, you have to be more careful. Sometimes of course, in the Heisenberg picture and other places, you need to solve operator equations. And oftentimes a good strategy is to say, well, let me just forget that they're operators and solve them as if they were C numbers, like a classical problem. And then you solve it, and then you get a formula. Well, then what you can use is you can say, well, that formula may or may not be right because I didn't take into account operator ordering. But I can take that as a guess for what the solution is to the operator problem, and then substitute back in and check it. And it may work. Or if it doesn't work, it might fail because you can see there's an operator ordering you need to diddle with, and you can figure out how to do that. So this is a strategy for solving operator equations, which is actually works out in quite a number of cases. I'm going to try to see if I can clear up the screen a little bit. Good. There we go. All right. Okay. So this then is the construction of the coherent states. All right. Now, allow me to, coherent states raise an interesting question, which is what happens to their time evolution. Let me go back by sketching things in phase space again like this. And let me change notation. Let me take A and replace it by X naught, and take B and replace it by P naught. So I'll write it this way as W of X naught P naught applied to the ground state 0 gives us what I'll call X naught P naught. And the geometrical picture in phase space is clear. I've got X and P like this, and I move it up here to a new location that has location is X naught and P naught. And I want to think about this as being initial conditions for either in the quantum problem for a wave packet, or in the classical problem, it'd be initial conditions for classical motion. So anyway, this is the coherent state x0, p0. Now the question I'd like to raise is, what happens if I apply the unitary time evolution operator for the harmonic oscillator to this x0, p0 state? In other words, how does a coherent state evolve in time? You may be aware, a moment ago, I explained that the expectation value of x and p were 0 for the ground state of the harmonic oscillator. You may be aware, you probably did this in your undergraduate course, the expectation values of position and momentum are also 0 for all of the excited states of the harmonic oscillator as well. And it sounds like a strange result, because when the amplitude is high, it's swinging back and forth. Why do you get a 0 expectation value? And the reason is you're talking about energy eigenstates, and an energy eigenstate means a precisely defined value of energy, which in some sense, I'm just speaking intuitively now, in some sense means that the time is completely undefined. So when you take an expectation value of the position operator with respect to an energy eigenstate, it's sort of like averaging over time, as if you took the classical oscillator, and you took the x motion and averaged it over a lot of orbits in time. Well, obviously the answer would be 0, even though there's large excursions are balanced out on the other two sides. And that's more or less what happens in the quantum problem also. But now what we've got is something that's not an energy eigenstate. It's a coherent state that has a non-zero value, expectation value of x and p. And so the question we want to pose now is, what happens to that if we take that as an initial condition for the harmonic oscillator? It's an interesting calculation to do. By the way, a calculation like this was first carried out by Schrödinger in 1926 or 26 at the latest. It may have been 25 even, he did it. And I'm doing something using a more fancy method using operator techniques, but the basic idea was done by him. Well, in speaking of the time evolution of this coherent state with these expectation values, we know some of the answer already, because we showed in the last lecture that in the harmonic oscillator that expectation values follow the classical orbit. So if I take this as initial conditions for a classical orbit, the x0 and p0, then what we know is that those expectation values will follow the classical orbit, which is a circle, which I can draw probably not very well, but there we go, there's a circle. So at some later time, we know the expectation values are going to be x of t and p of t, which are determined by the classical motion. Now that, and we also know that the angle that's carried out here is just the time t itself. Okay, we don't know, however, that the final quantum state is whether or not it's still a coherent state. Moreover, we don't know what its phase is either, even if it were a coherent state. So to answer those questions, we need to actually solve the quantum problem. And that's what I intend to do now, is to actually solve the quantum problem and actually work out what this u of t on x0, p0 is. By the way, we can introduce complex variables. Z0 is equal to x0 plus ip0 and its complex conjugate for z0 bar. This is the same thing that we've done earlier. These are the complex classical coordinates. The only difference is these are now the initial conditions. And reinterpret the phase plane as the real part of z and the imaginary part of z for the two axes. And if so, we get the same picture, but it's just labeled differently. We get real part and imaginary part. We have an orbit like this, and we have an initial condition like this, which is a blob here, and it's given by z0 indicates the initial condition. Let's just define w of x0, p0 means the same thing as w of z0 when they're related by this transformation, just a different way of labeling the Heisenberg operator. And let's also write x0, p0, the state itself, as z0 is just an alternative notation for the same thing. So we can talk about this in terms of complex language as well as in terms of the real q and p, or x and p variables. All right. Now, the question then is, how are we going to evaluate this Heisenberg operator acting in the ground state? We want to evaluate that. How do we do it? Well, here's a way of doing that. Here's the z0 equations here. Let me remind you, there's also equations connecting operators, namely that the the annihilation operator is x hat plus ip hat over √2, and a dagger is equal to x hat minus ip hat over √2. All right. Now then the Heisenberg operator, to remind you, W of X0 P0 is equal to E to the I minus X0 times P hat plus P0 times X hat. That's just a definition we had on an earlier page. But we can solve these equations here for X0 and P0 in terms of Z0 and Z0 bar. And likewise, we can solve for the operators X hat and P hat in terms of the operators A and A dagger. And we can plug that in here and transform this exponent. And if you do, it turns into this. It turns into, I have to remember it now, it turns into E to the Z0 times A dagger minus Z0 complex conjugate times A. It's just algebra to transform that exponent using the inverses of these formulas. And I'll skip the algebra, but anyway, this is what comes out like this. So this is just rewriting the operators X hat and P hat in the exponent as linear combinations of A's and A daggers and collecting the coefficients, which of course we can do. Now, however, I want to use Glauber's theorem a second time. This time we want to let capital A operator be equal to Z0 A dagger and the capital B operator to be equal to minus Z0 complex conjugate times A. If we do this, then the commutator of A with B is equal to Z0 times minus Z0 bar is the same thing as minus the absolute value of Z0 squared. And then we have the commutator of A dagger with A, which is -1. So the result is it becomes plus mod absolute value Z0 squared. That's the commutator. This again is a C number, which therefore commutes with both A and B. And so the conditions of Glauber's theorem are met. And so if I write out Glauber's theorem then for this transformation of variables, then what I have is this, is that E to the Z0 A dagger times E to the minus Z0 bar A is equal to E to the Z0 A dagger minus Z0 bar A, all in the exponent, plus 1/2 times the mod Z0 squared. And again, this last factor is a C number, so I can split it off to its own exponential because it commutes with everything. If I then bring that over to the other side, then I now have an expression for the Heisenberg operator, which appears here. So we then have this useful expression as a WZ0 is equal to E to the minus 1/2 mod, let me write it out carefully. WZ0 is equal to E to the minus mod Z0 squared divided by 2 times E to the Z0 A dagger times E to the minus Z0 bar times A. All right. And this is a useful expression for the Heisenberg operator. Now, why? Because we want to apply this to the ground state of the harmonic oscillator to get our final coherent state. So let's do that. There's 3 factors. Well, one's just a number, but there's other two major factors here. Let's look at the last factor first. E to the minus Z0 bar times A applied to the ground state. If I expand out the exponential series, it's 1 minus Z0 bar A plus 1/2 Z0 bar squared times A squared minus and so on for the exponential series, all acting on the ground state. On the other hand, the annihilation operator A annihilates the ground state. So that term goes out. And so do all the higher power terms because they've all got A squared, A cubed, and so on, and they all annihilate the ground state. So only the one survives. And the result is that this first factor here, on the factor on the right here, does nothing to the ground state, and we can just ignore it for as far as the action of W in the ground state is concerned. Let's move on to the middle factor now. Let's look at E to the Z0 A dagger applied to the ground state. This will expand out the exponential series as the sum n equals 0 to infinity of Z0 to the nth power divided by n factorial times A dagger to the nth power acting in the ground state 0. Now, the A dagger is a raising operator. So if I apply it once to the ground state, I get the first excited state. If I apply it 3 times, I get the third excited state and so on. So A dagger to the nth power applied to the ground state gives me the nth excited state, although there's a normalization too. In fact, the correct formula, if you get all the factors right, is this, is that A dagger to the nth power applied to the ground state of the harmonic oscillator gives me the square root of n factorial times n, the nth excited state. This is using the phase conventions that I derived in the last lecture. The square root of n factorial comes from the product of the square roots of applying all these a's over and over again. So this is easy to establish just by the usual formula for the action of a dagger on harmonic oscillator states. But now you see, if I put this in here, this square root of n factorial cancels 1/2 of that n factorial there. And then this allows me to simplify this expression. If I then include the prefactor, which is just this exponential of a C number here, what we get is this, is the W of C0 acting on the ground state of the harmonic oscillator is equal to this prefactor, which I'll copy, e to the minus mod Z0 squared over 2. And then we have the sum from n equals 0 to infinity of Z0 to the nth power divided by the square root of n factorial times n, like so. And this is actually an interesting formula. This is the state Z0. This is the coherent state Z0. This is an interesting formula because it's an explicit expansion of the coherent state with the given expectation values of position and momentum as a linear combination of harmonic oscillator eigenstates. Then notice we didn't have to use any complicated formulas with Hermite polynomials or anything like that to make this come out. This shows you something else too, is that if you're in a coherent state Z0 and you ask for the probability Pn of finding yourself in the nth energy eigenstate, then this Pn is just the square of the coefficient of that state n, which is there. And so squaring the prefactor just gives me e to the minus mod Z0 squared. As I say, kills the 2 when you square it. Then you get 1 over n factorial here from that denominator getting squared, and then squaring the numerator here. You have to square the absolute value. So it becomes absolute value of Z0 to the 2n power, like so. And this is what's called a Poisson distribution. You can see that the sum on n equals 0 to infinity of these probabilities, P sub n, gives me this exponential prefactor multiplied by what's an exponential series, and they cancel each other out and give you just 1 for the total, which of course is what you have to have. So this is a characteristic. In statistics, it's called a Poisson distribution. This is relevant in quantum optics because, as I explained, coherent states, I didn't go into this in any detail, but it's a fact that coherent states are to some approximation characteristic of the quantum state of laser light. When you have oscillations in a cavity which leaks out through a semi permeable mirror at one end in a typical laser construction. And so what this is giving you then is the probabilities for the various energy eigenstates, which in this context are the numbers of photons contained in the mode of the laser beam, and it's a Poisson distribution. All right, now.
I have a question.
Yes.
So in our definition of the Heisenberg operator of Z0, how come we could apply the lowering operator first and then the raising one? If we did it the opposite way, wouldn't that change the coefficients and thus the populations?
Yeah, it would, but it would also change the order of the A and the B, and it would change the commutator of them as well. It'd swap the commutator.
Okay, so it would still come out to a Poisson distribution?
It would give you a correct formula, but it wouldn't be as easy to work with because now you've got to deal with the creations first and the annihilations second, which would be kind of a mess. But it wouldn't be wrong to do that.
Okay.
Yeah, good. That's a good question. I'm getting a lot of good questions in the last several lectures. It's really very, very nice, actually. I'm glad you're keeping up on things here. All right. So this solves the problem of expanding a coherent state as a linear combination of energy eigenstates. And that's most of the way towards working out the time evolution. The reason is now the time evolution operator applied to an energy eigenstate n like this is just equal to e to the minus I E n t times the energy eigenstate. You know that's how energy eigenstates evolve. And the En in this problem is just n plus a half, and the units we're using, that's all it is. So this is e to the minus I times n plus a half times t applied to the state n. So if I want to apply the unitary time evolution operator for the harmonic oscillator to the coherent state as Z0 as an initial condition, I can bring it through this entire series, and then the U just acts on the N. And what it does is it brings out this phase factor. You can see this phase factor has a phase factor e to the minus IT over 2 from the 1/2, which is independent of N. I can take that out of the sum. The rest of it is e to the minus INT, and I can combine that with the Z0 to the nth here. So if I do that, that's kind of how the algebra goes. If I do that, then here's what we find, is we get that U of t applied to Z0 is equal to e to the minus IT over 2. Then we have the e to the minus mod Z0 squared over 2. That's the C factor that didn't change. Then we have the sum n equals 0 to infinity. Then we have e to the minus IT times Z0 quantity raised to the nth power divided by the square root of n factorial times times n, times the state n. So that's what we get when we do that. Now then, up above on the previous page, I still have it here, is the expansion of the coherent state W of Z0 up here. This, of course, Z0 is an arbitrary position. We could replace it by anything we wanted. Notice in this final result here, I got e to the minus IT times Z0. Perhaps you remember when we were doing classical mechanics and complex variables, that the picture looks like this, is that if this is the Z0 and this is the Z of t down here, then the angle is just t like this. And this corresponds to the classical evolution, which is that Z of t is equal to e to the minus IT times Z0. That's just the rotation in the phase plane using complex variables. It's given by this. So if I use that classical solution for Z of t, you can see that it's actually appearing here in the quantum solution. It's appearing right there in this quantity raised to the nth power. Also, if Z of t equals e to the minus IT Z0, then the square of Z of t, absolute value squared, is equal to absolute value Z0 squared. The phase factor goes away. So this Z0 squared in the prefactor I can replace by Z of t without changing anything. And the result is this thing can also be written this way as e to the minus IT over 2 times e to the minus absolute value of Z of t squared over 2 times the sum n equals 0 to infinity of Z of t to the nth power divided by root n factorial times n. And this final sum here is nothing but the coherent state evaluated at Z of t, the final classical position. And so what we obtain then is a nice result, is that U of t applied to Z0 is equal to e to the minus IT over 2 times Z of t, where, and this is the result we were looking for, where the Z of t is the solution of the classical motion with Z0 as initial conditions. And what this shows you then is that the evolution of a coherent state under the harmonic oscillator Hamiltonian, that it remains a coherent state. The coherent state is centered on its expectation values are centered on the classical orbit. We knew that anyway from Ehrenfest type considerations, but in fact it remains a coherent state. And the only thing that changes is that it's got an overall phase factor of e to the minus IT over 2. And by the way, notice that if you carry this around a complete cycle of the classical motion, so that t is a period of the classical motion, then the Z of t returns to itself, but the phase factor does not. It goes into -1. So this means that evolving such a coherent state under the time evolution of the harmonic oscillator over a complete period of classical motion actually changes the sign of the state. It goes from its original state into minus itself. That minus itself is clearly related to the 1/2, which occurs in the quantization condition. And if you think about Bohr-Sommerfeld theory, that's related to the number of turning points in the harmonic oscillator. So all those things are all tied together. All right, this result is the main thing that I wanted to get as an illustration of some of the things you can do with coherent states, some operator techniques, and some of the neat things that can be done. There obviously are generalizations one might want to consider. What would happen if the initial state were not a coherent state, but were a squeeze state instead? Then it turns out that at the evolution, as it evolves, again, the expectation values have to follow the classical orbit. We know that. That's true for all initial conditions. But if initial condition is a squeeze state, it turns out that as it evolves, it doesn't remain a squeeze state, not of the same type anyway. In fact, what happens, it kind of breathes in and out. If it's squeezed in the sense that the delta X is in a sense too small initially, what happens is after, let me get it right, whether it's after a half period or quarter period, it's after a quarter period, it is actually spread out the other way. It's too big. And after a half period, it comes back together again and it's just squeezed as it was at the initial time. At 3/4 of the period, it's too big again. And then when it comes back to the initial time, it's squeezed again. So it breathes in and out. That's what happens with a squeeze state. And those types of problems can be analyzed by more sophisticated formalisms than the ones that I'm using here tonight. All right, that's actually all I want to say about harmonic oscillators and coherent states, at least for now. So are there any questions about that before I move on to another topic? Harmonic oscillators. There's all kinds of, harmonic oscillators are wonderful. There's all kinds of wonderful things you can do with them at the same, and they're used in an enormous number of applications. And they're very fundamental, for example, in modes of fields and quantum field theory and so on. At the same time, they're rather special systems, and they have many special properties that don't carry over to other oscillators, even one-dimensional oscillators. Most oscillators have properties that are not like the harmonic oscillator. It's too special, and don't trust any paper that says, "Oh, I've got a theory and I haven't proved it, but look, I exemplified it with a harmonic oscillator and it works there." Don't believe any paper that says that, because harmonic oscillators are too special. They need to do it for something more general than that.
So does that mean a coherent state can only exist in a harmonic oscillator potential?
No, because a coherent state is just a state. It can exist anywhere. I mean, you can make it as a wave function for anything you want, but it only has this simple time evolution under a harmonic oscillator.
Okay, I see. So in another potential, it would decohere.
It sure will. In fact, it'll rather quickly. In most practical problems, it kind of spreads out all over the place pretty soon and doesn't look like a wave packet at all.
Okay, cool. Thanks.
I mean, it depends on the scale of the potential. You know, wave packets spread, and so there's a question of the spreading. How does it compare to the scale length of the potential? But if you try it in a typical atomic or molecular problem or something, it's likely to survive for roughly half a cycle before it's kind of blown all over the place. That's kind of my experience anyway. Let's see, there was something I wanted to say about that. No, it slipped my mind. All right, so I want to move then on to the next topic, which is path integrals. Very briefly, path integrals are an essential element of this course. There's something that everybody ought to know about. They constitute, in a sense, an alternative formulation of quantum mechanics. And in that sense, they're very deep. They involve a very different approach to quantum mechanics than the usual one, which is based on the Schrödinger equation and Hamiltonians as the generators of time evolution, as we presented it in these lectures. And as we'll see in the case of the path integral, the formalism is ultimately based on Lagrangians, ultimately classical Lagrangians. So we'll see hopefully tonight how that works out. So the story of path integrals begins with the story of the time evolution operator, which we called U of t comma t0 in our earlier discussions of that quantity. I'm assuming you remember what that is, but in case you don't, I'm going to summarize for you some of the results that we derived earlier. And I just have to find my summary page here. And here it is. So let me go over the properties of the time evolution operator as we worked out earlier. We call it U of t comma t0 with the initial time t0 and the final time t. One of the postulates we make is that if the initial state of the system is psi of t0, then the final state is related to the initial state by a unitary operator or by an linear operator, which we call U. That's the definition of U. And we postulate that U is unitary and that it satisfies certain other properties. I've listed out 6 of them here. It has the initial conditions that if the initial and final times are identical, then the operator is the identity, fairly simple property. It has the composition property that if you multiply it, combining interval t2 to t2 comma t1 with interval t1 to t0, you can just drop the t1 in the middle and you get the u of t2 comma t0. It obeys a Schrodinger equation, which is that if you differentiate with respect to the final time times IH bar, the answer is the same as the Hamiltonian multiplying u. Now here, for generality, I'm allowing the Hamiltonian to be a function of time. But if the Hamiltonian is independent of time, then the time evolution operator simplifies and depends only on the elapsed time, the difference between t and t0. In fact, it's given by e to the minus I elapsed time times h over h bar. And usually we simplify the notation by just writing u as in terms of a single parameter, which is now understood to be the elapsed time, not the 2 clock times t0 and t. And then the time evolution operator is just written this way. For time independent problems, that's how we do it. All right, this is a summary then of the main properties of the time evolution operator. Now then, I'll put that aside for a moment. Now, what we want to focus on tonight is what's called the propagator, or rather the word propagator is used for a number of different objects. And I'm going to just give you one of them tonight, a simple one of them. I call it K. And the propagator can be thought of as depending on two space-time points, a final one, which we'll call x and t, and an initial one I'll call x0 and t0. So K depends on x and t, and x0 and t0. And we'll put the final time first and the initial time second, as you see here. The definition of K is that it's nothing but the X space matrix elements between X and X0, the initial and final times of the time evolution operator U of T comma T0. So that's the definition of K. So let me box that here because we'll be using that. And by the way, I should have said that, but I should have said this earlier, but I'm presenting this material in the context of a simple Hamiltonian, which is a kinetic plus potential Hamiltonian. Obviously, I mean, X, you have to, I'm assuming here that X is a meaningful variable here. So it really has spatial degrees of freedom. Let's assume that the Hamiltonian has this form. And if it does, then the propagator is defined in this way as the X space matrix elements of the time evolution operator. I'm allowing the potential here to depend on time because there's no reason not to for what I want to do here. All right. So in a sense, the propagator is nothing but the X space representation of the time evolution operator is all it is. It just becomes a definite function. And its main properties are really just transcriptions of the properties of U itself, which are given over here. So let me go through some of these properties and transcribe them to show you what they look like in the case of K. Let's begin with the fact that U can be used to advance a state forward in time. How does that work for the propagator? To answer that question, I'll take this rule number 1 here and I'll multiply on the left by bra x coming in from the left-hand side. And so let me carry that out down here. So we get the scalar product of x with psi of t, and this is what we mean by the time-dependent wave function psi of x and t. But by the definition of the time evolution operator, that's the same thing as x on the left, u of t comma t0 in the middle, and then psi of t0 on the right-hand side. Like that, it's a matrix element like so. Now allow me to insert a resolution of the identity in between the last pair of factors here using the variable of integration x0. And if I do, this turns into an integral dx0 of x u of t comma t0 x0, that matrix element, and then x0 times psi of t0, like so. And if we do this, you see the first factor is the propagator, k of xt semicolon x0 t0. And the last factor is the initial wave function evaluated at x0 comma t0. X0 here is a variable of integration. Of course, it looks like an initial condition, but it's actually a variable of integration. The t0, on the other hand, is an initial time which is not integrated over. So this is how the propagator, that is to say, this function is used to advance wave functions in time. It's an important property, so let me write it down again, leaving behind all the mess we used to derive it. So let me write it down. The formula is this: is that psi of x and t is given by an integral over which you might call initial condition x0, spatial condition only. The propagator k evaluated at xt in x0 t0, like so, times the initial wave function psi of x0 t0. Okay, so let me box that because this is how propagators are used to advance wave functions in time. This formula has an interpretation in terms of Huygens' principle, an intuitive idea developed by Huygens a long time ago. Huygens was mainly thinking about light, but it works like this. Let's suppose you've got some wave field at time t0. And what I'm drawing here is perhaps a phase front of a wave. There would be other phase fronts also, let's say, at the given time, but this is just one of them. His idea is that the wave field at the final time is a superposition of little wavelets, which are emitted from the wave at the initial time. So I take each point of the wave at the initial time, and when I think of that as emitting little waves that radiate out from that, and they radiate out in time. And we let this evolve for some amount of time. And then the final wave is the linear combination, linear superposition of all these little wavelets. Oh, and I forgot to say that the wavelet, which is radiating from some point on the initial wavefront, is weighted by the value of the wave field, the psi of x0 t0 of the initial wavefront at that point. So then these add up and destructively or constructively interfere and give you a new wave field at time t, like so. And the waves are carried forward by this. Huygens realized that would be a way of doing this. Well, that's just what this is here. The psi of x0 t0 is the weighting of the little wavelets. The little wavelets themselves are actually the propagator. That's what that is. This is the source of the origin of the propagator, and this is its field point, in effect, at a later time. And by adding all this up, we get the total wave field psi at the final time. Now, I just mentioned that because it just gives you an intuitive a picture of what this formula means, and I think it's worthwhile to have such a picture. All right, so this is the property of the propagator, which corresponds to number one, the initial value property. Let's look at property number two. I'm sorry, not the initial value, the property that's used to advance wave functions in time. What I just wrote down is how this is expressed in terms of the propagator k. Let's look at number two, which is the unitarity. I'll skip that. Let's move on to number three, which is the initial conditions. So what does that say? So initial condition says that if I take k and evaluate it at xt0, semicolon, and x0 t0, that is to say where the two times are identical. By the definition, that's x and x0 ket sandwiched between u of t0 t0, which however is the identity operator. So that's just the scalar product of x with x0. And that's the same thing as a Dirac delta function, delta of x minus x0. So this is the initial value property of the propagator. If the initial and final times are equal, then we get a delta function in the initial and final x's. So that takes care of item number three. Let's talk about item number. There's a composition property for number four, which I won't write down, although it's straightforward to do. It just involves integrals over products of propagators. Let me move on to number five, which is in effect the evolution equation or Schrodinger equation for u. How does this work out for the propagator? Well, it goes like this: is if I apply IH bar ddt to the propagator k of xt semicolon x0 t0, like so. This, by the definition of k, is IH bar ddt, the matrix elements between x on the left and x0 on the right of u of t comma t0. But this IH bar ddt, the only t that appears here is right there. So I can bring this into the matrix element and let it act on the u. And if I do and use the Schrodinger equation for u, this turns into the x and x0 sandwiched around now the Hamiltonian h of t times u of t comma t0. And if my Hamiltonian is the Hamiltonian I spoke of earlier, for simplicity, let's assume it's a simple 1D kinetic plus potential problem like this. I'll allow the v to potential to depend on time if you want. I can bring this h out of the matrix element if I replace it by the differential operator corresponding to this in the X representation. So this turns into minus h bar squared over 2m d squared dx squared plus v of x and t, acting on x and x0, sandwiched around simply u of t comma t0. All right, but that's k. This is k all over again. So the net effect of this is we have a differential equation for k. It's I h bar partial with respect to t of k of x and t and x0 t0 is equal to the Schrodinger operator, which I'll write out explicitly here, plus v of x and t applied to k of x and t semicolon x0 t0. This is in effect the Schrodinger equation, which is satisfied by the propagator, regarded as a function rather than as operators. So things to notice about this is that the Schrodinger equation applies only to the final position in time. That's what the ddx is, it refers to the final x, the ddt refers to the final t. The initial position in time go along simply as parameters. So k of x and t then, semicolon x0 t0, actually is a solution of the time-dependent Schrodinger equation, which is parameterized by x0 and t0. And how is it parameterized by that? It's parameterized by the initial conditions that k of x and t0, when the final time t is equal to t0, I wrote this down earlier, this is the Dirac delta function, delta of x minus x0. So one of the ways of thinking about the propagator k, and sometimes this is useful, is to say that this is the solution, that k is the solution of the time, you can call it psi if you want to, of x and t. It's psi of x and t, a solution of the time-dependent Schrodinger equation, which satisfies the initial conditions that at t equals 0, psi is a delta function, t equals t0, psi is a delta function concentrated at x equals x0. Now, that's oftentimes useful. Now, that initial psi is a rather singular initial condition. It's not normalizable, and so it doesn't represent physical states. Nevertheless, if you think about it as being in some approximation as having a wave field that's highly concentrated, maybe not exactly as a delta function, but highly concentrated in a narrow spatial region, then it's clear that it has high momentum components because of the uncertainty principle. Delta x is small, so delta p has to be big. So it's an initial wave function, in effect, that has very high momentum components, and the limit they go to infinity as we really go to the idealization here. And so when you turn on time, what happens is that those very high momentum components basically blow up. They've got arbitrarily high velocity. And so they blast in an arbitrarily short amount of time, they fill up all of space. And what that means is that the propagator is actually a rather singular looking function. Its behavior as t approaches t0 from above is actually a rather singular looking behavior, but you can understand it in terms of in some sense, like a classical ensemble of particles that include momenta going all the way out to infinity, but all concentrated at x equals x0, and then you turn on time and look what happens, boom. All right, so anyway, that's the propagator. All right, so those are some of the main properties of the propagator, which follow from the, in a rather straightforward way, from the properties of the unitary time evolution operator. To proceed with the propagator, I think it helps to have an example. So let me work one out. And naturally, the example we'll do is the case of the free particle, because it's not only it's not only doable, but it's also useful in practice. Actually, finding the propagator for most potentials or most Hamiltonians is not an easy task, because if you could solve it, in a sense, you've got a complete solution of the quantum mechanics, certainly for the time evolution. However, if you know how wave functions, arbitrary wave functions evolve in time, well, you see k allows us to evolve an arbitrary wave function in time. That's why knowledge of k, by doing the integral, that gives you the evolution of an arbitrary initial state. If you know the time evolution of an arbitrary initial state, you can Fourier transform it in time and obtain the energy eigenfunctions. So in other words, knowledge of the propagator basically gives you everything you need to know about the solution of the quantum problem. And so for that reason, it's typically hard to find. Nevertheless, in the case of the free particle, we can find it, and it turns out to be useful, as I just mentioned. And so let's work it out, and it'll give us some practice in not only evaluating propagators, but also seeing a specific answer. So let's take the case where h is equal to p squared over 2m, and I'll put a hat over the p here because this is an operator here. I'm going to hat over the h2 if you want. So this is the case where the Hamiltonian is independent of time. And so let's just let t be elapsed time now, and let's define k of x, x0, and t now with only a single time to be equal to the matrix elements between x and x0 of u of t, where t is now just the elapsed time. This is probably the easier thing to do for Hamiltonians, which are independent of time. Get rid of one of the time parameters. Or if you like, we set the t0 equal to 0, it amounts to the same thing. So let's work this out for the free particle. So this is going to be x sandwiched around u of t is e to the minus I. The h is a p hat squared over 2m times t divided by h bar times x0. Looks like that. The momentum operator p hat there. We need to evaluate this matrix element. The way to do that is to insert a resolution of the identity and momentum between the last two factors. This is a straightforward calculation here. And so what we get is integral dp, and then we get x, and then we get e to the minus I, p hat squared times time t divided by 2m h bar in the middle. Then we get momentum state p there, the momentum bra p, and then x0 cat like that. That's what this integral turns into, like this. Okay, so I'm just doing a derivation of working out what this k is. And the first step is to insert the resolution of the identity. Now this operator, which involved the Hamiltonian with the momentum operator p hat, is now acting on an eigenstate of p with eigenvalue p, which appears here without the hat because that's a C number. So p hat acting on an eigenstate of itself just brings up the eigenvalue, and that means what we can do is remove that p hat, remove the hat, I mean, and just replace that by p squared, which is now a C number. Having done that, this entire factor is just a C number and can be taken out of the matrix element x and p that's left over here. Now the xp matrix element and the px0 matrix element are just plane wave or free particle matrix elements. So this turns into integral dp of e to the minus I p squared t over 2m h bar times the xp scalar product, which is e to the I xp over h bar divided by square root of 2 pi h bar. And then the px0 one is e to the minus I x0p over h bar divided by the same square root. And if I clean this up a little bit, it becomes integral dp. We have e to the minus I p squared t over 2m h bar plus I x minus x0 times p over h bar. And this is all divided by 2 pi h bar denominator here that came from those two square roots. Okay, so I'm just doing the integral now, or I'm just about working out the matrix elements to get an integral. This integral is a complex Gaussian of exactly the same type you had in last week's homework, and it's straightforward to work it out. And if you do, I'll just quote the answer. You get this, you get the mass divided by 2 pi I t h bar, and then an exponent, which is e to the I over h bar, the mass m times x minus x0 quantity squared divided by 2t. And that's the free particle propagator x comma x0 comma t, like so, for the free particle. And let me box that because that's our nice result from this calculation. All right. Based on what we said, this thing ought to approach a delta function as t goes to 0, delta function x minus x naught. And in fact, if you understand carefully enough what you're doing and what happens when you integrate this against a test function, you can see that it actually does do that. But the the limit is quite singular. You see there's a 1 over square root of t prefactor here. The phase factor, of course, has a magnitude of 1. But the 1 over the square root of t means that as t goes to 0, the magnitude of this thing is going to infinity. Also, the 1 over t, which appears here in the exponent, means that as t goes to 0, this thing oscillates more and more rapidly. Becomes the scale length goes to 0. The wavelength goes to 0 as t goes to 0. That is to say, unless x is very close to x0, that's what saves you, you see. If you look at it more carefully, what you'll find is there's a little lobe around x equals x0 that has a width that it goes like the square root of t and has a height that goes like 1 over the square root of t. And that's the behavior that gives you the delta function as t goes to 0. In any case, it works out if you do it right. This actually does have the limit of a delta function as t goes to 0. Okay. So that then is the propagator for the free particle. And we'll kind of post that as a result and come back to it later when we need it. What I would like to do now is to address what do we do about propagators when we can't solve the Hamiltonian so easily. Maybe there's potential around. And so this is what leads to the path integral. So this is also going to be a derivation of the path integral. I'm going to do this derivation in the context of a simple one-dimensional problem with a Hamiltonian p squared over 2m plus v of x. I won't even let it have a time dependence because there's no need to. The reason is that all the essential ideas of the path integral come out from working through a simple 1D example like this. So I might as well simplify it as much as possible. And we'll do this, we'll work with this 1D example. What we want for the propagator then, it's going to be k of x and x0 and t, because this is a time independent Hamiltonian. And this is, as before, is just x and x0 sandwiched around u of t. And a u of t, of course, can be written in terms of the Hamiltonian as e to the minus I t h over h bar. Okay, where h is now this more complicated Hamiltonian. Our strategy for analyzing this problem and getting something useful out of it is to take this u of t, where the time interval t need not be short, it could be a long time interval. And we'll break it up into a large number of small time intervals. That is to say, let's let capital N be some number which ultimately we'll think about letting it go to infinity. Let's define epsilon is equal to t over n, which is a kind of a delta t, which goes to 0 as n goes to infinity. So that we basically divide our time interval up into a large number, capital N, of small time intervals we call delta t or epsilon to remind ourselves that it's small, which go to 0 as we let the number n go to infinity. Then this u of t, which appears here, can be written this way as u of epsilon dot 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 times u of epsilon, where there are a grand total of n factors in here. Like so. Because if you combine u of t1 with u of t2, these are elapsed times, and so they just add and give you u of t1 plus t2. This is also obvious from the expression for time independent Hamiltonians for the propagator that the times just add when you multiply the propagators together. All right, so we're just now adding these small times epsilon n of them to create the total time t. Now then, the next step is that we insert resolutions of the identity between each of the factors of u of epsilon. There are n factors, so there's n minus one slots, or n minus one slots between the u's, between the initial and final ones. So that we can now write, and this is still with no approximation, we can now write the propagator k of x, x0, and t is equal to an integral over the intermediate resolutions of the identity dx1 up to dxn minus 1 of the following: the final x, u of epsilon, x sub n minus 1, x sub n minus 1, u of epsilon, x sub n minus 2, and so on, dot, 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 down to the last one, which is x1, u of epsilon, x0, like so. You can't really argue with this. All we're doing is just is just multiplying operators with resolutions of the identity to convert them into matrix elements. All right. But now notice what we've got is we now have matrix elements of time evolution operators in which the elapsed time is small. And in fact, by letting n become large, we can make this elapsed time as small as we like. Let's look at this u of epsilon. We can write it this way as e to the minus I epsilon over h bar times t plus v. That's kinetic plus potential. The t is p squared over 2m, and the v is the potential v of x. So this is just the Hamiltonian, but the point is that the epsilon is small here. Now the question is, here's the question that arises. We have, as we had earlier with Glauber's theorem, what we've got here is an exponential, and now we've got a sum of factors in the exponential, one of which depends only on momentum, and the other of which depends only on x. That's similar to what we had with Glauber's theorem. These two factors don't commute with their commutator, however, so we can't use Glauber's theorem. It's too bad because it would be nice if we could, but we have to do something else. And here's what we're going to do. We're going to take advantage of the fact that epsilon is small. In particular, if I expand this in a power series in epsilon, what I get is 1 minus I epsilon over h bar times t plus v plus order epsilon squared, just carrying it through first order. On the other hand, if I took the product operators, e to the minus I epsilon over h bar times t, multiplied times e to the minus I epsilon over h bar times v, like so, and expand those, then the first factor is 1 minus I epsilon over h bar t plus the second order term. And the second factor is 1 minus I over epsilon h bar v plus the second order term. And if I multiply those series together, what we get is 1 minus I epsilon over h bar t plus v plus order epsilon squared, which agrees with what we had up here with the exponential of the t and the v combined together up in the exponent. Now these two expressions are not the same. We know they're not because of just what we went through with Glauber's theorem and so on. They're certainly not the same because t and v don't commute with each other. But what we have found is they actually do agree when epsilon is small. They do agree to first order in epsilon. The order epsilon squared terms will be different. But we're going to let epsilon go to 0 by letting capital N go to infinity. And the question then is just the first correction term enough to get an accurate answer, to get a correct answer? And the answer to that seems to be yes. But I can tell you that if you want to do it rigorously, if you're a mathematician and you want to do it rigorously, you've got a lot of work to do. I mean, there's a long, long history of trying to make this rigorous, and it's not a trivial thing at all. And so what I'm going to do tonight is to do an especially bad hand-wavy, physicky job of justifying it. But it basically amounts to ignoring the fact that these order epsilon squared term corrections are of higher order, in the hope that those corrections will not matter when we take the limit that n goes to infinity. In fact, this turns out to be true. Okay, so this is the strategy then. So if we do this, then each of these factors between a pair of x's of the u of epsilon can be factored like this. So let me bring this down then. So let's look at one of these factors, and let's look at, oh, by the way, the final x here, we can also call it x sub n if you want, just by, in other words, let's take the final x and just define it to be xn, because that gives it a uniformity in the use of subscripts on x. We go x0, x1 up to, counting the x's up to the last one, x sub n, like this. Notice that only the intermediate ones, x1 to xn minus 1, are the variables of integration. The initial one, x0, and the final one, xn, are not. Those are fixed. Those, in fact, are parameters of the propagator, which is on the left-hand side here. All right, so let's take one of these matrix elements. Let's write it as x sub j plus 1 on the left, and then u of epsilon in the middle, and then x sub j on the right. And if I factor u, I make an approximation here that epsilon is small, and factor u into a factorization like this, and insert a resolution of the identity of momentum in the middle there. And this becomes the integral dp of x sub j plus 1. And then for the kinetic energy part, I get e to the minus I epsilon over h bar times p hat squared over 2m times momentum state p. And then the next matrix element is momentum state P, e to the minus I epsilon over H bar times the potential V evaluated at X hat times XJ on the right-hand side. And let me try to disentangle that from the circular blobs and stuff. I hope you can see that. I hope I'm not writing too small. I just inserted this resolution of the identity between the kinetic energy factor and the potential energy factor, and otherwise just wrote them out. Now, this P hat is acting on an eigenstate of momentum, so we can remove the hat here. And this X hat over here in the potential energy is acting on an eigenstate of itself for the eigenvalue X. So again, I can remove the hat on that X. And if I do, then these things in the middle, which were operators, now become C numbers and can be taken out of the matrix elements. When you do that, the integral that you get is almost exactly the same thing that we had earlier in the free particle, the evaluation of the free particle. I'm sorry, I didn't say this right. Let me do it correctly. I'm gonna correct something I said a minute ago. The P hat is the operator here, but it's acting in an eigenstate of itself with momentum C number P. So I can just lift the hat and replace P by just P hat just by P itself. In the case of the potential, the X hat is the operator, but this didn't get written out very clearly, but that's X sub J. So this is between X sub J plus 1 and X sub J here on the two sides, because it's one of these factors that appears up here. And so this, when I remove the hat here, what I should do is I should replace X hat by X sub J, the eigenvalue of the ket that it's acting on. All right, and if we do this, then what we get is an integral, which is almost the same integral we had earlier when evaluating the propagator for the free particle. It becomes e to the minus I epsilon over H bar times P squared over 2m. And then we get plus I over H bar times X J plus 1 minus X sub J times P. And then we get minus I epsilon over H bar times V of XJ. And except for the V of X sub J, it's the same integral we had before. And so the integral turns into this. It's the square root of, and T is replaced by epsilon here. Except for that, it's the same integral. It's M divided by 2 pi I epsilon H bar, e to the I over H bar, mass M, xj plus 1 minus xj, quantity squared over 2 epsilon, minus I over H bar, epsilon times V of xj. It turns into that. Okay. And that is one of the factors here, and of which there's n factors. And there's n minus 1 integrations. So to get k, what I need to do is to multiply together these factors. These factors are only approximate when epsilon is not really 0. You multiply these factors together and then take the limit as n goes to infinity. And if we do this, then, oh, and by the way, when we multiply those factors together, the prefactors, of course, are just going to multiply these things here. And the multiplying the exponents, and x, of course, the product of exponentials is equal to the exponential of the sum. And so if we do this, what we obtain is an expression for the propagator, k of x, x0, t, is equal to a limit in which n goes to infinity of the mass m divided by 2 pi I epsilon H bar raised to the n over 2 power. An integral dx1 up to dxn minus 1. And then we have the exponential of the following. It's I over H bar times the sum, j equals 0 up to n minus 1 of the mass m over 2 times xj plus 1 minus x sub j, quantity squared over epsilon. Let me put a square brackets here. Minus epsilon times v of xj, like so. curly brackets like that. And this is something that you can regard as a discretized version of the path integral. Path integral arises when we let n go to infinity. And unfortunately, I don't have time tonight to explain to you why it's called a path integral, but that will be the first step in the next lecture. And we'll do some work and analysis on this and understanding it, and to simplify the notation and so on, and do some applications. Okay, so that's all for tonight as far as I got an introduction to the path integral. Are there any questions about this?
Could you also show, like, just on top the previous page, just like,
This is where I was doing the integrals.
yeah, thank you. I just wanted to take a look. Yeah, thank you.
So each of these integrals here, except for the potential energy, which just kind of goes along for the ride, is really the same integral that we had in evaluating the free particle propagator. Most of it comes from doing the momentum integration for the taking care of the kinetic energy. And the factors and everything on the Gaussian integral is all exactly the same. But this is only for one of the factors, and then we need to multiply them together. There's n factors, as you see here, multiplying them together. So instead of getting an exponential of one term, we get an exponential of the sum of these terms. And that's just what this sum is here. You see, I factored out a common factor of I over h bar. This thing here is just the prefactors. Each one of these factors has the same square root, but there's n of them total. So that's where I got the n over 2 power there. And this is just the same integral of the resolutions of identity in X space that we started with when splitting up the propagator into small time increments.
Uh-huh. So in doing all of this, we've used the propagator in position space. So I'm guessing, is there also a momentum space propagator?
Yeah, you can do this in a momentum space, and it's interesting to see how things transform from position space to momentum space in the process of doing propagators and doing path integrals.
Is that useful in any way? Like,
Oh yes, it's definitely useful. It's definitely a part of understanding propagators. There's a couple of good books on propagators. I cited them in my notes. One is Feynman and Hibbs, which is good in a certain way, and another one is Larry Shulman's book, which is good in a very different way. They're both good books. I love Shulman's book. I learned so much from it in reading it. It was one of my favorite books. It is honored, you might say, by being one of the most frequently stolen books out of physics libraries. And he told me about this because the thieves, even thieves want to learn about path integrals, I guess. So what's starting to appear here is a classical Lagrangian. So I'm done tonight, so I won't say anything new except for that, but except to promise you that when we meet on next Tuesday, I'll explain that in more detail. Are there any other questions tonight about any of it?
How would you show that the propagator is unitary? That doesn't seem very obvious to me.
Yeah, that's actually a good question. Of course, it sort of has to be, because all we did was we broke those unitary operators into a product of a large number of small unitary operators. So it still has to be unitary. You could question whether this approximation we're making at small time, would destroy the unitarity. And that would certainly be a valid question. Yeah, so that's an important question, and it's certainly answered in the literature on path integrals, but I don't think I can't do it justice tonight to tell you about it. It's something one can do once you get the path integral together, to check that it's not only unitary, but you also want to check that it has the composition rule.
Right. Okay.
Okay. Any other questions? All right, if there's none, then I shall stop.
Actually, there is. I'm trying to think about the propagator kind of like more intuitively. Like it seems like a propagator is some type of matrix element
Yes,
between X
yes,
and X naught.
yes, that's what it is.
But when you mention that X naught is like an initial condition, we're integrating over initial conditions. I don't really understand what that means. Like,
Okay.
and
Okay, so X naught is an initial condition in the following sense, is that the propagator can be thought of as a wave function, the solution of the time-dependent Schrodinger equation, in which the initial condition has the wave function completely concentrated at X naught. So it's like it's a wave function, it's an initial wave function, which is a delta function. Now, that's not normalizable, but never mind that. It's think of it as an initial state that's highly concentrated in some limited region of space. It's a limit or an idealization of that kind of physics. So in that sense, it really is an initial condition for a quantum problem. Okay. Now, however, in addition, once you know the propagator, you can use it to propagate forward arbitrary initial conditions. They don't have to be delta functions. It can be any initial wave function psi of x at t equals t0. And the reason is that you can just think of that initial wave function as a linear combination of delta functions spread over all space, and then just let the k do each one of them. Each one of them propagates as a k. And then adding them up is the integral formula that gives you how k moves an initial wave function forward. Do you follow me on that?
wait, okay, I have to.
So when you use k to move a wave function forward, you have to carry out an integral. And if you think about it in terms of Huygens principle, each one of those little wavelets is k. That's the k with an initial point, which is a point in the initial wave field. And you integrate over all those points x0 to cover them all. And then you add up all the waves that result from those little wavelets radiating from those points.
I see.
Okay. To say that the x0 is an initial condition it's an initial condition in the sense of quantum mechanics, because as I say, you're imagining an initial wave function which is highly concentrated around x0. That's what your psi of t0 is. In that sense, it is an initial condition. However, that's not an initial condition for a classical orbit. The classical picture is rather different. In fact, the quantum picture shows you that if you localize the initial wave function very, very narrowly around x0, the initial momentum is completely undefined. So it goes out to very high momentum values. So
Right.
this is like not a classical particle, but rather an ensemble of classical particles, all of which have been confined together in a very small region, but their momenta are all over the place. Some of them have extremely high velocities. And then you snap your hands and you turn on fingers and you turn on time and boom, they go. The high velocity ones really go. So that corresponds to so what would happen to the classical ensemble is it would explode. It would just be all over the place instantly.
Yeah.
And that's what happens to the quantum wave function too. It blows up too. It's blam. It's all over everywhere instantly.
So another way I'm thinking about this is like when we do the overlap, to find the propagator, we're basically doing the overlap of the final x and the time evolved initial condition x naught.
Yes, that's right.
So and then we're integrating over this x naught. So then is this initial x naught, is that also that's x naught at t naught at time t naught, and then that's time evolved?
Well,
is that how it's supposed to?
Well, the propagator is parameterized by both x naught and t naught. So, I mean, if you have a definite propagator function, I mean, the x naught and t naught just have a value. But what that value represents is the initial condition for a solution of the Schrodinger equation, which was highly concentrated around x naught at time t naught. By the way, I should have said this, but there's language that people use, which is useful to some extent in describing the propagator. They say the propagator is the amplitude to find the particle at position x at time t, given that it was at position x0 at time t0.
Oh, yeah.
Okay, that's a way of stating it, and it's useful to keep that language in mind, even though it really isn't very accurate, because these are unbound, and it isn't so much at xt, but it's the density, and and there's issues about that. But the basic picture that's conveyed by that, the intuitive picture, is valid, and it's quite useful, I think.
Yeah. I think that makes more sense. Yeah.
Yeah. That's a good way to. That's a good phrase to keep in mind. It's the amplitude to find the particle at the final time x at final time t, given that it was at x0 at time t0.
Right.
Okay.
Okay. Yeah. Thank you.
All right. If you ever get a chance, read the first chapter of Feynman and Hibbs. It's very interesting in terms of it's Feynman's intuition about quantum mechanics. It's very interesting. I'll touch on it a little bit in my next lecture. All right. Are there any other questions?
I have one last question.
Yes.
So you said that solving for the propagator means that you can determine the time evolution of arbitrary states.
Yeah, if you know the propagator, you can.
If you know the propagator, so that is the same. That's equivalent to like diagonalizing a Hamiltonian and finding the spectrum of a Hamiltonian.
Well, not all at once, but if you can do the integral, to propagate the wave functions forward in time. So now you know the time evolution of any wave function. Let's say you can do that. Now then, if you wanted the energy eigenfunctions, then what you do is you Fourier transform the time evolution. So in doing that, you see, if you do the Fourier, so if you have a discrete spectrum, let's say you have only bound states, it means that the Fourier components of the time evolution of any initial state whatsoever are those Einstein frequencies connected with the energy eigenvalues. Because that's the e to the minus I omega sub nt. You see where omega n is E n over h bar. So by looking at the Fourier spectrum, you find the omega n's, and multiplying by h bar, you get the energy eigenvalues.
I see.
And
but
then
the problem.
Yeah, go ahead.
Should the problems be there? Should the problem's computational complexity be like equivalent? Like you don't, for certain classes of Hamiltonians, is it easier to do one method versus the other?
Yes, the answer is yes, but in terms of official complexity theory, I can't answer that. I don't know if one is from a complexity standpoint simpler than another. People that do numerical work, of course, are always trying anything they can try to to shorten and simplify the numerical effort. And I can tell you that people actually do Fourier transforms of time evolutions, maybe not obtained by propagators, but obtained by other methods, time-dependent Hartree-Fock, all kinds of methods like this. And this is one of the techniques which is sometimes used for finding energy eigenvalue, ground states, and so on. There's a million ways of doing these problems. I think the trade-offs depend on the nature of the problem.
Thank you.
Okay, any other questions? All right, if not, then I can finally stop screen share. Hit the red one, and then stop recording. Thank you very much for your attention. I really appreciate all the questions tonight.
Thank you. See you on Tuesday.
Yep.
Thanks.
See you next Tuesday.
Thank you.